Hello and welcome everybody to this week's Infosys Chandrasekhar and Random Geometry Colloquium. Today we are very happy to have Ghosh from NUS, Singapore, who will give us a talk on stochastic geometry beyond independence. Over to you, Shubhro.
Thank you, Subhroshekhar, and also Piyush for your kind invitation. And I have never had the chance to visit TIFR in person, although I have wanted to for a long time. But let's make the best use of whatever opportunity we have here online. Okay, today I'm going to talk about stochastic geometry beyond independence, and oops. Okay. So the model I'm going to follow is that I presume that some of these topics are quite popular in India, so I would presume that some of the audience has some familiarity with some of these topics. So I will tend to go a bit fast and sort of more heavy on the main ideas and maybe a little light on the finer details, and I will be happy to answer any questions about the fine print as and when they come up. So please feel free to stop me and ask questions. So the most popular model of randomness in science is perhaps that of independent and identically distributed random variables. So the i.i.d. paradigm, so in brief, it is abbreviated as i.i.d. independent and identically distributed. So the i.i.d. paradigm has led to groundbreaking progress and a vast body of literature, including many ideas and methodologies that have become second nature for applications. And though there is scientific interest in exploring beyond the i.i.d. paradigm, progress in this direction mostly involves specific structure with a very limited or a very localized dependence. So for example, various kinds of Markov processes have been analyzed. And also some results have been obtained in the direction of independent but not identically distributed random fields, but dropping the independence assumption has really proven to be hard. And in general, lack of independence is largely believed to be an obstacle or a hindrance to be overcome, and many approaches involve trying to locate independence or approximate independence in the overall dependency structure. So we start with some strongly dependent model, let's say strongly correlated model, and then an important goal of the mathematical analysis becomes how to locate approximate independence within this overall dependency structure. Okay, so this is how many theorems are proved. But in this talk, we will take a different point of view. Namely, we will try to exploit the dependent structure in order to make substantive progress in natural questions in stochastic geometry and their applications. So in other words, in summary, we will try to make friends with dependency and not regard it as an enemy. So let's see how far we can get there.
Shubhro, are you going to carry independence with you? Would that be a special case, or is this a completely different approach?
No, so basically we are going to sort of look at the opposite extreme. So we will start off with some strongly dependent models from basically motivated by statistical physics. So these are, there is really no simple independence hiding inside these models, okay? But they are also relevant for various applications to computer science and machine learning, etc. So we will also refer to them as and when they come up.
So independence is not a special case for you?
Not here. So in other words, we will take these strongly dependent models and our goal will be to actually exploit the dependence. So kind of carrying the independence within it kind of defeats the purpose in some sense. Okay. So in this talk, we will look at some natural models of strongly dependent random systems. They are very well motivated by their origins in statistical physics. So what are these models? So these include determinantal processes or determinantal probability measures and critical points of random functions. So both are of importance for various reasons in statistical physics. So let's take a closer look at these two varieties of statistical physical models. So first, determinantal processes. So determinantal processes are models of random point sets that are governed by a determinantal structure. So I will come to the details of what this determinantal structure is in a moment. But first, a bit about random point sets. So any model of a random point set is characterized by its correlation functions, which are essentially the joint probabilities of having points at specified locations. So if you specify a bunch of locations to me, I will specify to you the joint probabilities or probability density of having points at those locations, and under good conditions or under some consistency conditions, this defines an overall random point sets over your domain. Okay. So to be more concrete, if alpha 1, alpha 2 up to alpha m are m fixed locations, then the m point correlation function, which we denote by rho m, is the joint probability density of having points at those locations alpha 1, alpha 2 up to alpha m in a realization of the random point set. So you can compare it to, let's say, if you take a real valued, or let's say you take an integer valued random variable, then you can talk about the probability mass function, which is essentially the probability of having the random variable take a particular value. Okay, so these are exactly the analogous things. And just like you can build sort of a discrete random variable out of its probability mass function, similarly you can build a point process out of these so-called correlation functions. So for example, what is the simplest example? The simplest example is to do independent points over a domain. Let's say, your favorite part of let's say the unit square in the two-dimensional plane. And then the m point correlation function is simply rho to the m, where rho is the mean density of points per unit area. So this is just an example, and let me now come to the determinantal structure. So the determinantal processes are models of random point sets where these correlation functions are precisely given by determinants, and these determinants are determinants of an m cross m matrix. For every m, you form an m cross m matrix at those locations alpha 1, alpha 2 up to alpha m, and you take the determinant of this matrix, and that gives you the correlation function. And the determinants and how are these determinants formed, or how are these matrices formed? They are formed by a kernel function k, which is the function that is kind of driving the determinantal process. So this kernel basically parameterizes the determinantal process, except that it's a general kernel function satisfying some positive definiteness conditions. So it's really an infinite dimensional parameter. But still, you can think of it this way: that determinantal point processes are random point sets that are parameterized by a kernel function k. And just some immediate observation is that if alpha I and alpha j among these locations are close to each other for some I and j, then under some mild continuity assumptions on the kernel k, this density rho m, which is given by the determinant of this matrix, that this determinant is going to be very close to 0, because alpha 1, alpha I close to alpha j implies in particular that the ith and the jth columns of this matrix are going to become close to each other. So the determinant is going to be small, and therefore the probability of having points at these locations where two of the locations are close to each other is small. So in other words, in determinantal point processes under some mild regularity hypothesis, it's unlikely to have points that are very close to each other. So thus a DPP penalizes points for getting too close to each other, and therefore naturally embodies a repulsive interaction between the points, but it does so in a very nonlinear and complicated manner. So which makes it very difficult to unentangle these dependence and look at some approximate independent structure. Okay. So DPPs are therefore effective in modeling situations where the sample points need to be very different from each other. So example, in diversity sampling, the population may be represented by points in some high dimensional feature space, and the kernel K incorporates the proximity between these points in the feature space. And this in turn encodes the similarity between different points that we want to sample from. In statistical physics, DPPs have their origins in the study of fermionic systems and random matrix eigenvalues, where they emerge as natural models for electrons and related particle systems. So here is some simulation for plots for i.i.d. point processes and determinantal point processes. And as you can see, the determinantal process is much more spatially homogeneous. So this has some connotations which, time permitting, we will have the we will have the occasion to return to. So random zeros and critical points. So these are models of random point sets that are given by zeros of random functions. Important class of examples include critical points, especially maxima and minima of random functions, since these are the zeros of their derivatives, which are random functions themselves. An important class of examples include zeros and critical points of random polynomials. So when the random function is a random polynomial, for example, polynomials with random coefficients like Gaussian coefficients. So here again is a plot of independently sampled points as opposed to zeros of a suitable Gaussian random function. Okay, and as you can see, once again, the zeros of the random function, they exhibit a much greater degree of spatial homogeneity than the i.i.d. points. In fact, it seems almost as if the zeros of random functions or DPPs have been obtained by simply taking a fine grid and perturbing the points randomly a little bit. Okay. But this is, of course, not the case. I mean, these are statistical physics models which arise in a highly complicated manner. So this observation brings us to the notion of hyperuniformity. So it may be observed that the distribution of points in self-repelling stochastic systems like determinantal processes or random zeros appears to be more uniform or more spatially homogeneous than independently sampled points. So this is indeed true. This spatial homogeneity is indeed true and can be rigorously understood by looking at various measures of spatial homogeneity. In fact, this can be exploited to obtain efficient quadrature rules in numerical analysis using these models of random point sets. Okay. So let me now jump into our first object or first sort of class of results that we are going to discuss in this talk. So these involve the model of Gaussian determinantal processes.
Shubhro, a quick question for you. You mentioned that these can be used for integration using quadrature method and all.
Yeah.
So that presupposes kind of a cheap way of generating samples from these determinantal processes. So are they kind of examples of models which are very easy to generate samples from?
Yeah. So for example, you can take, the eigenvalues of Gaussian random matrices are determinantal processes. So you just take a Gaussian random matrix and do a diagonalization, and that's it.
And that's cheap enough? That sounds pretty.
Yeah, I mean, depends on how many points you want, but you know, for quadrature, once you generate your quadrature nodes, you can use it for.
I see, yeah.
Many times, so it's just a one-time cost.
Right.
But also, it leads to very interesting possibilities. Your question. So thanks for mentioning this. So basically, when you do things like numerical integration particularly involving Gaussian, particularly involving DPP nodes, there can be, so of course your quadrature estimate is random because your points are random, and there can be actually, so if you are interested in the approximation, which is this random sum over the Gaussian or the DPP nodes, then actually there is a way to directly sample from these from this approximation, from this approximating sum. You can directly sample from it. So we have some recent work which we are wrapping up in that direction at this moment.
And so you get some limit theorems which are interesting,
Yeah. So you can show that these approximating sums converge to the true integrals, and then there are central limit theorems governing them, and you can obtain estimates on rates and so on.
So you get improved rate of convergence compared to uniform.
Yeah. Because of course, if you take uniformly random points, as we saw, there are some issues with them. There are clusters of points and there are holes, and of course, if you are trying to do quadrature with those, DPPs are going to be much better. Thanks. So in the analysis of DPPs, a robust parametric model with naturally interpretable parameter modulation is squarely lacking. So this relates to the point of the kernel K that we discussed before. So in principle, DPPs are parameterized by this kernel K, but the kernel K is just a general positive definite kernel operator, which is in general it's an infinite dimensional parameter, which is not that it's not that useful. It's only notion. It's only parametric in notion. So what we would really like is to have a sort of a parameter space having a small dimension that parameterizes your kernel and hence your DPP, such that, and not only that, we would also want to have meaningful parameter modulation. So when we modulate this low dimensional parameter, we should see meaningful and interpretable change in the random point set distribution. So that's our goal or motivating question behind studying Gaussian determinantal processes. So so we can compare this, for example, to the well-known models of exponential families in probability theory, or exponential random graph models, or ERGM, that are popular in the study of stochastic networks. So these are precisely sort of low dimensional, low parameter spaces that give rise to interesting models of stochastic networks or random variables. Okay. So we want to have something like that in the world of DPPs. So to this end, we propose the model of Gaussian determinantal processes, abbreviated as GDP, that will be indexed by the space of positive definite matrices of a given dimension, and we will refer to this parameterizing positive definite matrix as the scattering matrix. So this in turn would be a testing ground to understand the response of the spatial variable behavior of the random point process to parameter modulations in the space of scattering matrices. So there is this parameterizing positive definite matrix of low dimension, and we will modulate that parameter, and we will observe or we will try to understand what is the impact of parameter modulation on the stochastic geometry of the spatial point process. Okay, so that's our goal, and this part is based on joint work with Philippe Rigaud. So a DPP is parameterized, specified by the underlying kernel. So for specifying the Gaussian determinantal process model, we just need to specify the kernel. So the kernel is simply the d-dimensional Gaussian density with some positive definite covariance matrix sigma, which is our scattering matrix in this case. And of course, therefore, the kernel automatically has this particular form of Gaussian density. And notice that the kernel kxy is a function of x minus y, so automatically it's translationally invariant. So that's a desirable property that one might want to have for a fundamental model. The mean density of points in a DPP with kernel k is simply given by kx comma x. So the mean density of points in a Gaussian determinantal process is simply this normalizing constant 1 over square root 2 pi to the d times square root determinant of sigma. Okay. And notice that this mean density is constant because the process is translationally invariant, so the density of points doesn't depend on x. And what is our observation? So our observation consists of the points, all the points that are realized in a realization window of a ball which is in the shape of a ball of large radius r. Okay, so we take a ball of large radius r and we observe all the points of the GDP that fall inside this ball, and those are our observations or observed points. And our goal is to interpret the stochastic implication of varying the modulating parameter sigma in the space PD of d cross d positive definite matrices. And note that modulating sigma such that determinant sigma changes will lead to a change in the mean density of points, because the mean density of points was basically up to constants is 1 over square root determinant sigma. So if you modulate sigma such that the determinant of sigma changes, then this will change the mean density of points, and this you can detect very easily by estimating the average density of the observed points. Okay, so that's kind of a sort of a trivial transformation in this model, which we will mod out by. So therefore, we will focus on the interesting parameter changes, which is in other words, we will focus on parametric modulation that leaves the determinant sigma invariant. So in physical terms, in physics terms, this corresponds to shear mappings or shear transformations of the space. So a key family of parametric modulations that we will consider in this talk will be in the form of a spiked model in the space PD. So if this reminds you of spiked models of random matrices, you are not very far off from the target, because indeed we are sort of kind of closely related in terms of flavor to that sort of questions. So formally, we take a direction for the spike along which we will modulate. So this is a unit vector u and strength of modulation lambda. And we will consider a parametric modulation which is of the form, which is of this form, which you can see on the screen. So you put a strength of 1 plus lambda in the direction of u, but you have to keep the determinant of sigma constant. Imagine that you are starting from identity matrix sigma equal to identity and modulating it. So you pick this direction u and you put so let me maybe try to draw a picture. Sorry. Yes. Okay. So you start with sigma equal to identity and you are trying to modulate it. So you pick this direction u and you put a strength of 1 plus lambda along the direction u, but you want to keep the determinant fixed and the determinant of identity 1. So you want the determinant of sigma to be also 1. So you spread the cost uniformly along all the orthogonal directions to u. So this is how the model is constructed. Okay, so this is the spiked model in the world of GDPs. So sigma equal to lambda equal to 0 makes the sigma equal to identity, which is the isotropic model. So there is no directional bias in the dependency structure of the points. Whereas lambda positive introduces a directional bias in the direction of u. And we want to understand how exactly this directional bias operates in the cloud of random points that we generate. So lambda bigger than 0 corresponds to a spiked model that introduces directional bias in the strength of the dependency structure. So the dependence, in this case, the repulsion between the points is much stronger. For example, much more long-ranged on the scale of 1 plus lambda in the spike direction of u. So if you think of lambda to be very large, then in order for 2 points to be decorrelated, if you are taking 2 points, if you are considering 2 points and if you are moving them further apart to make them decorrelated, then if you are moving along the u direction, you have to move very far along the u direction, because the strength of the dependence is much stronger along the u direction, and in fact it is on the scale 1 plus lambda. On the other hand, the dependency in the directions orthogonal to the spike is much weaker and decouples to almost independent behavior at relatively short length scales if the signal strength lambda is large. So okay. So given these observations, let us try to.
Sorry. So when you say it depends on the scale of 1 plus lambda, I mean, like, can I think of it as some kind of like a correlation length?
Yes. Exactly. That's what we mean. Okay. So let BT. So now given. So this is the sort of the mathematical or the stochastic geometric observation. And now we want to use this observation to sort of look at our observed points and try to check if there is a directional bias in the dependent structure of the point. So if a spike lambda is present, or whether it is actually isotropic and all the fluctuations that we are seeing are due to pure random noise. So for this, we denote by BT to be the Euclidean ball of radius t, and then x1, x2, xn is the observed points. So basically, we construct these observed in some sense this test statistic sigma hat. So you don't really need to go through the details of what this the precise algebraic expression. What I would like to draw your attention to is this sum, which is of the form xi minus xj times xi minus xj transpose. And basically, it is a pairwise it's a pairwise sum, and the sum is only over close by neighbors which are closer to each other than a threshold r, and we are coming in a moment to what this threshold r needs to be. But notice that these pairwise contributions among the points is also does not really depend individually on xi or xj. It only depends on the difference between the observations xi and xj. So in some sense, you do not really need to know the identities of the precise points xi and xj. You can, so in some sense, it allows you to make observations that are agnostic to the identities of the individual observed points and only look at their differences from their neighbors. And this allows you, and make only local measurements because you're only measuring in a local neighborhood of size r. And this allows you to construct an estimator sigma hat, which actually is a consistent estimator of sigma in the sense that expectation of sigma hat actually in the limit as of large number of observations, it gives back to you sigma. Okay.
Sorry, one thing. So when you say the volume, is it just a regular Euclidean volume or the number of points in the point process that?
No. Regular Euclidean volume.
Okay.
Regular Euclidean volume. Okay. And you can do a usual bias variance trade-off in this situation, and that in order to determine the sort of the optimal value of the neighborhood threshold r, and it turns out that you just need to take r equal to square root d log n. So this is the optimal value of the parameter, which gives you sort of the best bias variance trade-off, and you can use this to estimate sigma efficiently in the limit.
Sorry, Shubhra, that's again. This term looks very similar to what would like maximum of n to the power d Gaussian points. I don't know in real. Has it got anything to do with extremum of Gaussian? No. Okay.
Not. But it also looks like many other things.
That's true. That's true.
Yeah. But if someone does a very fine-tuned analysis like minimax rates and so on, probably Gaussian maxima of Gaussian fields will turn up at some point.
Okay.
But,
Thanks.
Not yet. Okay, so testing for directionality in GDP. So we want to test for directional bias in the dependency structure of the observed points against a null hypothesis of isotropic dependence. So essentially, we want to test whether the dependency structure is just isotropic, so sigma is identity, versus whether there is a non-trivial lambda along some direction u. And if so, in other words, we want to detect the presence of a spike. And this we can do by looking at the size of this estimating matrix sigma hat, the size of the operator norm of this matrix, and we can detect with high probability if a spike in the regime if the spike is above the threshold this. So this is expressed in terms of d and r, where r is the size of the observation window. One can also write this in terms of the d and n, where n is the total number of observed points. And actually, if you do that, you would observe that, roughly speaking, in expectation, n is of the size of r to the power of d. So actually, in terms of n and d, this threshold on lambda might look like many of the objects that people are familiar with in this kind of literature. So for example, this r to the d over 2 inverse is basically 1 by square root n, right?
So is there a sharp threshold phenomenon in terms of lambda, or?
I mean, this is really, our paper basically introduces this model, and all these things are basically a virgin territory. So
okay.
Please feel free to stake a claim to any part of this.
Okay.
So and if you conclude that there is a spike, so then you would be interested in finding the direction u of the spike. So that's the next natural question, and no wonder that the leading eigenvector of sigma hat it can be shown to be a consistent estimator of the true direction u of the spike. Okay. This can be used to perform dimensionality reduction and the analysis of directionality in data. So how do we do that? So the problem of dimension reduction is one of the central problems in applied mathematics. So it has led to significant methodological progress. So two important paradigms are principal component analysis and its derivatives, or PCA, and the entire suite of methods involving the Johnson-Lindenström's lemma and related random projection-based techniques. Okay, and there are many other. I mean, dimensionality reduction is such a fundamental problem. So, so herein we will try to use the GDP model to perform dimensionality reduction. So first, let me try to motivate why and how the GDP model can be. We can even consider the GDP model to be useful in this respect. So roughly speaking, dimension reduction involves finding a low dimensional subspace, or equivalently a small number of significant directions. This is the first keyword, directions, which contain most of the information about a usually high dimensional data. So that's the first thing. And thus, the problem of dimensional reduction and the problem of detecting directionality in data are closely related. And notice that in the GDP model, we are also focusing on uncovering directional structures in observed points. So in the most canonical model for dimensionality reduction, which is the principal component analysis, we are interested in the directions of maximum variability, which is obtained, which is by, in other words, the direction of maximum variance. Okay. And these are obtained by taking the principal eigendirections of the covariance matrix obtained from the data. But we view the dimensionality reduction problem more generally, where dimension reduction will be performed by finding the optimal directions with respect to some other feature as opposed to variance. So if we maximize the directions of maximum, if we optimize the directions of maximum variance, we get principal component analysis. Instead, we will take some other measures of variability or differences, and we will try to optimize or maximize those, and presumably those are going to give us other alternative methods of dimensionality reduction. So the GDP model is exactly going to give us that, because because remember from our discussion on the GDP model that this direction of in the spiked version of the GDP model, the direction of the spike precisely entailed to the direction of maximum repulsion among the points. Okay. So we use the GDP model as an answer for proposing a direct dimension reduction methodology. We compute which is as follows, and we proceed as follows. So we have these observed bunch of points, presumably in high dimensional space, and we want to perform dimension reduction on those points. So how do we proceed? So notice that this estimator sigma hat, this could be computed for any collection of points. It doesn't really need, in order to just compute the sigma hat, it doesn't really need to come from a GDP model. It could be computed for any collection of observed points. What that means for any collection of observed points is a different question, but you can compute it. So given a collection of observed points, we compute sigma hat mechanically, and then we perform a singular value decomposition of sigma hat and project the data points onto the principal eigendirections of sigma hat. Okay. So, for example, in the case of a single spike, so in the case of a single significant direction, you project onto the top eigendirection of sigma hat, and this should uncover the low dimensional directional features in the data. So the idea is that after projecting onto these principal eigendirections, this gives us a low dimensional, these projected points gives us a low dimensional representation of the original data points, and we are going to work with those, and those should reveal to us some underlying structure of the data. So, so in this kind of direction, of course, the proof needs to be in the pudding. So here is the proof. So we applied this methodology or this approach to some standard data sets where where dimensionality reduction, which are significant for dimensionality reduction. So this is the Fisher's iris data set. So there are 3 varieties of points here, and you project onto a two-dimensional space. And so on the left panel, you see the results from PCA. So you can see that the projection points, it sort of separates the black points very well from the other 2, but the red and green are still fairly entangled. For the GDP, we do it using the sigma hat obtained from the GDP model. And there you can see that, of course, the black is well separated here as well, but the red and the green are much better separated than what you get in the PCA model. Okay. Similarly, here is the Wisconsin breast cancer data set. So once again, we compared the PCA and the GDP, and you can see that the black and the red have sort of much less overlap in the using the GDP approach. And for this particular data set, it should also be commented that these black points are kind of the more virulent varieties. So these are the bad points which we want to absolutely identify. So it really helps that the GDP approach actually concentrates and clusters them very closely together without much scatter. Okay. Okay. So so this was our sojourn into the Gaussian determinantal process model. So let's now switch gears and let's discuss a bit about the geometry of fluctuations in hyperuniform systems. So hyperuniform systems we have already alluded to earlier. It involves this kind of sort of models where there is a strong degree of spatial homogeneity, for example, compared to the uniform or independent random points. Okay, but we will sort of make this concept more concrete in a short while. So just to sort of set up notions, a random field X is a collection of random variables indexed by ZD. So you can also do random fields indexed by RD or other points. So, but lattice is sort of most convenient for laying out the ideas clearly. So let's just do lattice in this talk. And the random field is translation invariant if the joint law of these random variables is invariant under shifts in RD. So if you in ZD, so if you pick a J naught and you do I going to I plus J naught on all the xi's, then under these transformations for a fixed J naught, the law of this collection of joint law of this collection of random variables is remains invariant. Okay. So, so what is one simple example is a 0, 1, each xi is 0 or 1 value. It takes value 0 or 1. So you can think of each lattice site in ZD to be occupied or unoccupied. And in this case, it gives you a particle system, right? Or a point process on ZD. Another class of examples, just to show the generality of the scope of examples that this kind of formulation captures, is Gaussian processes. So you can imagine x's to be Gaussian processes indexed by ZD in having certain correlation structure. And next we come to an important character in our story, which is the concept of local mass. So CL is the hypercube of size L in ZD. So it's the box of size L in ZD. So let's say side length L. And QCL is simply the sum of all the xi's where I falls inside this ZD. So if this was a 0, 1 valued xi, so a point process or a particle system, this QCL just counts the total number of points inside the box. But for Gaussian processes, it gives you the sum of the Gaussian variables falling inside this box, and so on and so forth. So we call this object total local mass. So X, the random field, is said to be hyperuniform if variance of this local mass is little of the volume as L goes to infinity. Okay. So, what is the significance of this? So imagine that all the xi's were i.i.d. If all the xi's were i.i.d, then a simple computation will convince you that this variance is actually equal to some constant times the volume of CL. Okay. Some constant C0 times the volume of CL if independent. So hyperuniform means that you are little of the volume. So your fluctuations are less. You have suppressed fluctuations compared to independence. Okay. So there are various other ways of making sort of concrete the notion of hyperuniformity. So under translation invariance, you can consider, so here is an equivalent notion which is valid under translation invariance of the model. So if the model is translation invariant, then you can consider the covariance function, covariance of xi and xj. So this is a function of I and j, and under translation invariance, it's actually a function of I minus j if it's translation invariant. So then you can look at the Fourier transform of this function, of this covariance function, and that's called structure function in statistical physics, which we denote by S. And hyperuniformity basically corresponds to the statement that the structure function vanishes at the origin in the frequency space. Structure function is the Fourier transform, so structure of the covariance function. So structure function lives on the Fourier space or the frequency space, and hyperuniformity basically corresponds to the notion that the structure function vanishes at the origin in the frequency space. And our goal in this section is to understand the fluctuations of the field of local masses in the hyperuniform system, in particular the directional geometry of these fluctuations under the impact of anisotropic decay in the structure function S. So the important notions are fluctuations of the local mass in a hyperuniform system, in particular the directional geometry of these fluctuations, and under anisotropic decay of the structure function. So since the system is hyperuniform, the structure function decays at the origin, and if you are in dimension, so if you are in dimension 1, basically there is only one way of decay, unless as long as S is continuous. But if you are in higher dimensions, dimension d bigger than 1, then the function S can approach 0 in multiple different ways depending on the direction of approach towards the origin of the frequency space. So if there is this kind of anisotropy in the decay of the structure function at the origin, then what kind of impact does it have on the fluctuation of the field of local masses? So the fluctuation of the field of local masses is actually the same as the particle is the same as the fluctuation of particle number in the setting of point processes. And this is of independent interest in statistical physics. And this is based on joint work with Karthik Adhikari and Joel Lebowitz. And actually, because this object is so important in statistical physics, our first main result was sort of a tight estimate of the order of the fluctuation, order of this variance, directly as analytical integrals in terms of the structure function.
So one question.
Yes.
What's is there a good example of such a hyperuniform system? Like, is easing model beyond the transition with a plus boundary conditions?
So let me give a simple example. So this is in the continuum, but random matrix eigenvalues. Okay. Random matrix eigenvalues are hyperuniform, and in general, if you take any determinantal process, and this would also include discrete, any determinantal process which is whose kernel is a projection kernel, and under mild assumptions on your
spanning tree,
let's say,
spanning
for example, on Euclidean lattice, for instance, spanning tree on Euclidean lattice, and these things, these are hyperuniform. Okay. So this formula is of actually of considerable interest in statistical physics, but today we are concerning ourselves with the directional geometry of fluctuations. So we will not spend much time on this, and instead directly jump ahead into the considerations of the directional geometry of fluctuations. And we obtain the correlation structure between local masses in neighboring hypercubes. So if you take a single hypercube of side length L and you grow L, and you might be interested in the fluctuations of this, you might also consider two hypercubes which are adjacent to each other, abutting each other, and then both of these are growing to infinity, let's say, at the same rate. then what is the joint correlation structure of the local masses in these two adjacent abutting hypercubes as L goes to infinity. Under sort of a wide, in many usual models which people like to work with, there is often some kind of decorrelation as L goes to infinity. Okay, so the correlation structure is only sort of finite scale and local. So we will see that for our systems, this is not the case. So so this is some technical sort of notation, which in the interest of time, let me skip and let me directly bring you to the sort of the main result for this section in some sense, and maybe I'll try to explain you by picture what we mean. So we keep in mind that we are exactly trying to analyze something like this. We are trying to analyze two adjacent, the fluctuation of local masses, the correlation structure among those, when the two hypercubes of size L basically sort of overlap at the boundary. Okay, so if they are so in 2 dimensions, for example, there are only a limited number of ways they can overlap. The simplest thing is that they do not overlap and they float away from each other to infinity. So this is this case where the covariance structure is 0. So they are decorrelated as L goes to infinity. Then the next simpler overlap structure is when you have they sort of overlap only at a vertex. So that's the simplest kind of overlap that you can have. And then then the next more complicated ones is that you overlap in an actual edge. And the next higher level of overlap is actually you overlap with, the two squares are the same, so we are back to variance. So the interesting object is this item number 1, which basically gives you the correlation structure. So the assumption is this kind of spectral decay. So this kind of decay on the structure function. So of course, this quantity blows up. The denominator blows up at the origin of the frequency space, and the contention is that the contention is that, and this can be only finite if the structure function vanishes at infinity, vanishes at the origin of the frequency space. Not only vanishes, but vanishes in a certain way, vanishes fast enough so that this integral is finite. Once this is the case, you can our result kicks in, and it basically tells you that the covariance structure, and this actually also subsumes the case of the variance. So the covariance structure, first of all, generally speaking, we think of hyperuniform processes as sort of self-repelling. But interestingly, here, the sign of the covariance is not always negative. It depends on the dimension of the simplex at which characterizes the overlap between the two hypercubes. And then the second important part is that L is going to infinity, but the covariance doesn't blow up with L. It is of order 1 as L goes to infinity. So there is really some very strong rigidity or very strong frozen behavior, even if you increase the sort of the length scale of your system. Okay. Okay. So this was about, and so this is some diagram to illustrate it. So maybe in the interest of time, maybe let me jump ahead into the next section, which is about maximum likelihood problems with constraints and their connections with random zeros. So maximum likelihood methods constitute one of the most canonical approaches to inferential problems. So traditional maximum likelihood consists in maximization of a likelihood function based on given observations over a set of possible distributions. So there are a possible set of, so there is a parameterized space of distributions, and then you find the optimal parameter value which maximizes your likelihood within this parameterized class of distributions. What we would be interested in this talk is maximum likelihood with constraints. So suppose we have n independent observations, x1, x2, xn, and k constraining functions, f1, f2, fk, with constraints mu1, mu2 up to mu k. So in other words, each fi is a function of x1, x2, xn, and we have some, for each I, we have some predetermined notion of what the value of fi should be, which is mu I, and we want to find a weight distribution on the x's, so that the expected value of fi at the points x1, x2, xn according to these weights should be equal to mu y. Okay, so our goal is to really recover this weight distribution. So we consider w1, w2 up to wn to be a weight vector corresponding to the x's, and we want to maximize the likelihood product of wi's, subject to the constraint that the expected value of the fj according to this discrete weight distribution on the points x's is mu j. So mu j is our preconceived notion of what the average value of fj should be, and we want that to be true, and we want the wj's to be the maximum possible, to be the weight distribution that maximizes the chance subject to this constraint of the expected value for fj. Okay, so an important instance is of the constraints are the moment functions fj equal to x to the j, if it is a real valued observation, and it is like higher dimensional observation, you can take mixed moments. And then it is really the fact that we are, let's say we are having Gaussian data and we have some preconceived notion about what the mean should be. So we want to fit the data so that we force the data to have the right mean, or force the sort of the response distribution to have the right mean. Okay. So for the sake of definiteness, we will consider the basic setting when the data points are i.i.d following some distribution x, and the constant is just the mean of the observations. So we just do one constraint, so k equal to 1, and this is our optimization problem. So once we have this function, we know this function f. As soon as we have the observation points x's, we compute the hi's, which are f of x's, and then our constraint is that summation on the weights is that summation wi hi's should be equal to 0. Okay, if under the when our preconceived notion of the mean value of f is 0. If the preconceived notion of the mean value of was different from 0, then what we would do is that we would simply replace this 0 by some mu which is not equal to 0. Okay, so these are the two cases. So in terms of hypothesis testing, you can think of the null hypothesis being this empirical mean to be equal to 0, and the alternative hypothesis to be the empirical mean to be some pre-specified mu which is not 0, and we want to find out which is the truth. Okay. So the empirical measure is our candidate for the distribution of f of x. We formulate this as a Lagrangian optimization problem. No need to go into the details of that, except for the fact that the optimal value of the Lagrange parameter is actually a critical point of the polynomial f lambda, little f of lambda, given by this. And notice that the hi's are random, and since the data xi are independent, the hi's are independent. So since the hi are random, so this should be hi. So since the hi are random, this is actually a random polynomial, and the optimal Lagrange parameter lambda hat is a critical point of this random polynomial. Okay. So this establishes connections to random critical points and random zeros. And if under the null hypothesis, so if our presupposition about the mean value of f is indeed correct, then a lot is known. So this is usually always the well-researched case in the literature. And then you can get all kinds of good things: asymptotic normality, chi-square distribution, regularity of the candidate estimated distribution, and everything. So I'm not going to the the fine points of this in the interest of time, and also not necessary for our discussion. However, to understand, to have a complete picture of the constraint likelihood maximization, we need to understand the so-called energy landscape of the model in statistical physics terms. So in other words, we really want to understand, we really need to understand what happens when this constraint is actually not the truth, but our presupposition is wrong or misspecified, and it's a mu different from 0. And let me quickly summarize the result. In this case, this is joint work with Chowdhury and Gangopadhyay. So it's a very there are two or three observations. The first observation is that the optimal weight distribution essentially has an atom as n goes to infinity. So it's degenerate, it's not regular as in the sort of the correctly specified case. There is no chi-square limit for the log likelihood, unlike the correctly specified case. In fact, there is no discernible limit. This we can show. And the key driver of this phenomenon is to analyze very minutely the behavior of the optimal Lagrange parameter lambda hat, and actually what we do is that we obtain an expansion of this critical lambda hat by considering it as a critical point of the random polynomial, and this expansion gives the location. The expansion gives out the fact that there is a degeneracy, and it also gives us the location and the size of the atom. Okay, and this analysis can also be used for solving other related problems. And let me end by another figure which we all like. So this is the figure. So these black points is the weight distribution, optimal weight distribution f hat, when we are in the correctly specified case. And so you can see that it's a very regular weight distribution. The weights are almost uniform. So along the y-axis we plot the weights. The weights are almost uniform, and they're very small, of the order 1 by square root n. On the other hand, the red curve is the plot of the optimal weight distribution in the misspecified case, which is our case of interest. And you can clearly see a very large outlier, an atomic weight, which is gradually taking shape as n is going to infinity. So with this, we thank the audience for their patience in listening to the discussion, and to Piyush and Shubhajit once again for their kind invitation and the opportunity to present our work. Thanks.
Thanks, Shubhra, for this very nice talk. Let's thank our speaker. So I think, yeah, we have time actually. It's a very well-timed talk, so we can have some questions from the audience if they want to.
I have a small question actually.
Yes.
Go ahead. Yeah.
So the way that we have some result related to the roots of the random polynomial, roots of a polynomial function, some bounds on that and in the region in complex plane. So is there any results regarding that for the random functions?
I'm
Roots
sorry,
of the
I
random.
didn't get your question. So could you please So we analyze the critical point or a certain sort of extremal critical point of this random polynomial. But if you have some specific, I mean, what do you want to understand? So you want to understand the values of this random function?
Suppose we have a normal function, not a random function, a function, and we are trying to give some bounds on the roots in the complex plane, or how many the number of the roots in a bounded region. We have some results for the normal functions,
Yeah.
but
So first of all, this is slightly different. So in the usual analytic random analytic function or random polynomial literature, what people do is that they make the coefficients to be random and independent usually, right? And then they study these under various distributional hypothesis on the coefficients, on the random coefficients. Here it's a bit different. Here we have here the roots are random. So the independence is in the root. So if you consider the coefficients, they are like elementary symmetric functions in these roots. So they're super complicated. The coefficients are super complicated. They're all dependent to a very high order. So this is a slightly different beast. It's a different kind of random polynomial. The kind of questions you are asking are, of course, of interest from a sort of a general random polynomial point of view. But we analyze this in this particular paper for this to understand the behavior of the log likelihood in the regime of large n. And for that, we really precisely needed to understand this particular extremal critical point. So that's what we focused on in this paper. But you are absolutely right that the questions you are asking are perfectly legitimate questions for this kind of I mean, the roots might be a bit simple because the roots in this case are independent, but you can ask other usual random polynomial type questions, and I believe they are going to be pretty interesting. Anything about the value, I mean, this law of this random polynomial is basically the log likelihood. Okay, so anything meaningful you can say about it is probably going to have implications for the bigger problem.
okay, thank you.
Okay, so if there are no further questions, let's thank our speaker again. So, okay. Thanks a lot, everybody, and we'll see you next week. Thanks a lot for